If we trace the roots of modern physics, especially the physics powering lasers, computers, atomic theory, and quantum mechanics, we eventually reach a single moment in history that changed everything: the moment Max Planck introduced the revolutionary idea of energy quanta. It sounds like a small phrase, a minor concept, maybe even a technical point hidden inside an old, dusty textbook. But in truth, this idea shattered the foundations of classical physics, rebuilt the universe at its most fundamental level, and forced scientists to rethink the meaning of energy, matter, light, and reality itself. Understanding why Planck introduced this idea takes us into an exciting story filled with scientific failure, desperation, creativity, and courage. To appreciate the significance of Planck's quantum proposal, we need to step back into the scientific world of the late 1800s. At that time, physics was considered almost complete. Many leading scientists believed the big mysteries of nature had already been solved. Electricity and magnetism were mastered by Maxwell's equations. Mechanics had been perfected through Newton's laws. Thermodynamics had established its rules about heat, energy, and work. Even the nature of light seemed explained. Most physicists were confidently teaching their students that the universe behaved in predictable, continuous, logical ways, like a well-oiled machine. Yet beneath this calm surface, a huge problem was lurking. It was called the Blackbody radiation problem. And solving it would change everything. A black body is simply an idealized object that absorbs all radiation and emits light purely based on its temperature. When heated, it glows red, then orange, then white. Scientists knew how this looked in the lab, but they couldn't explain it mathematically. Every formula they tried either matched the data at low frequencies or high frequencies, but never both. One part of the curve would fit perfectly, but the other side would blow up into nonsense. Classical physics insisted that energy could vary smoothly, that light and heat could be absorbed or emitted in any amount whatsoever, no matter how tiny. It was a simple idea. Energy was continuous, but this continuous energy assumption led to a disaster known as the ultraviolet catastrophe. According to classical predictions, a glowing object should emit infinite energy at high frequencies, meaning everything around us should be constantly blasting out deadly ultraviolet rays. That obviously wasn't happening. Something deep, something fundamental was wrong. Max Planck, a German theoretical physicist, was drawn into this mess almost reluctantly. He wasn't trying to invent a new theory. He wasn't trying to shake science. He certainly wasn't trying to start a revolution. His personality was conservative, disciplined, and respectful of tradition. He believed in classical physics. He believed nature was smooth, continuous, and elegant. But he could not ignore the problem that had humiliated the biggest names in physics. By 1900, experimentalists like Lummer and Pringsheim had collected extremely accurate measurements of black-body radiation curves. The data was crystal clear, and still classical theories collapsed. Planck tried everything in his mathematical toolbox. He tried adjusting constants. He tried new equations. He tried modifying old formulas. Nothing worked. The curve just wouldn't bend the way the real data did. Then came his breakthrough. Instead of assuming energy was continuous, Planck made a daring, almost shocking mathematical assumption. What if energy could only be emitted or absorbed in tiny, fixed packets? Not in any arbitrary amount, but in discrete steps, like rungs on a ladder instead of a smooth ramp. It was a completely alien idea at the time. Nobody had ever proposed such a thing. It went against centuries of scientific intuition. But when Planck used this concept to derive a formula, the curve matched the experimental data perfectly. He published his result on December 14, 1900, and with it, the quantum revolution began. This idea of energy quanta meant that light wasn't just a continuous wave, as classical thinkers believed. Instead, light behaved in chunks, each chunk carrying an amount of energy proportional to its frequency. The higher the frequency, the larger the chunk. Planck gave this chunk size a mathematical constant, now called Planck's constant h, one of the most important constants in the universe. At first, Planck didn't fully grasp the philosophical meaning of his discovery. He considered the quantum idea a temporary trick, a convenient tool to fix one stubborn problem. He didn't believe nature was actually built out of quanta. He just needed the math to work. But physics disagreed with him. Albert Einstein, just 5 years later in 1905, took Planck's idea seriously, very seriously. Einstein argued that light itself was made of these energy packets, later called photons. This was a deeper, more radical interpretation, and it opened the door to the photoelectric effect, atomic models, and eventually quantum mechanics. Einstein's courage pushed the quantum idea from a mathematical trick into a physical reality. The idea of energy quanta was shocking because it suggested the universe wasn't smooth. It wasn't continuous. It wasn't behaving in the calm, predictable way classical physics assumed. Instead, nature was grainy, jumpy, and quantized at microscopic scales. At the smallest levels, things didn't change gradually, they changed suddenly in jumps. This concept later led to the idea of quantized orbits in atoms, quantized vibrations in molecules, quantized energy levels in electrons, and quantized probability waves in quantum mechanics. Yet in 1900, all of that was still hidden inside Planck's first insight. To understand why this idea was so revolutionary, imagine if you told a classical physicist of that era that energy isn't smooth. Atoms only absorb certain energies and reject others. Light exists as both waves and particles. The microscopic world behaves differently from the macroscopic world. Nature has a smallest possible chunk of energy, a minimum step size. It would sound insane, it would feel like science fiction, but this is exactly what Planck's discovery implied, even if he didn't fully intend it. The idea of energy quanta forced physicists to confront a new kind of universe, one where classical logic broke down at small scales, one where certainty gave way to probability, one where particles acted like waves and waves acted like particles. This was the birth of modern physics. Planck himself later said, "I did not think much about it. I was desperate." Those words reveal how groundbreaking the moment truly was. The discovery wasn't born from confidence or belief. It was born from intellectual honesty. Planck was willing to follow the math, even when the math dragged him into new territory. By introducing energy quanta, Planck cracked open a door that no one could close again. Once physicists walked through that door, they discovered quantum mechanics, atomic theory, nuclear physics, semiconductors, lasers, quantum computing, and countless other breakthroughs. And it all began with one bold step: Planck questioning the assumption that energy is continuous. In this single move, he changed the future of science forever. The moment Max Planck introduced the idea of energy quanta, he unknowingly lit a fuse that would burn through the walls of classical physics. What started as a desperate attempt to fix a single, stubborn problem soon grew into a revolution that scientists couldn't contain, and many didn't even want to accept. The world of physics in the early 1900s was comfortable, predictable, almost smug in its confidence. People believed the universe worked like a smooth machine. They believed every change happened gradually, and that everything could be measured with perfect precision if you just had the right tools. Planck's idea didn't just bend these beliefs, it snapped them in half. After publishing his solution to the Blackbody radiation problem, Planck himself felt uneasy. He wasn't a rule breaker by nature. He didn't set out to be a rebel. He had enormous respect for the classical world view and hoped that, eventually, someone might show how his quantum hypothesis still fit into the old framework. What he didn't realize was that his tiny mathematical assumption had exposed cracks running deep into the foundation of classical physics, cracks that other scientists would soon pry open. Einstein was the first to understand the explosive potential of Planck's idea. When he read Planck's 1900 paper, he didn't see a temporary mathematical fix. He saw a fundamental truth about the nature of light. If energy really came in discrete packets, Einstein reasoned, then light itself must be built out of packets, little bundles that carried energy in fixed amounts determined by frequency. This was the birth of the photon, though that word didn't come until later. Einstein used this insight to explain the photoelectric effect, a phenomenon where light striking a metal surface ejects electrons. Classical physics insisted that the intensity of the light should matter most. Brighter light should knock more electrons out. But experiments showed something stranger. The frequency of light mattered more than brightness. Only high-frequency light, like ultraviolet, could liberate electrons, no matter how dim it was. This made no sense unless light carried energy in packets, each packet having a minimum amount of punch required to free an electron. Einstein wrote this in 1905, a year now called his annus mirabilis, and immediately shook the scientific world. But even then, many physicists resisted. The idea that light came in particles seemed ridiculous after Maxwell's equations had so elegantly shown that light was a wave. How could something be both a wave and a particle? The question haunted physics for decades and eventually became one of the central mysteries of quantum mechanics. So while Planck had proposed the idea of quanta, it was Einstein who first gave it a deeper physical meaning. But the quantum revolution didn't end there, it widened. Planck's formula worked beautifully for Blackbody radiation, and Einstein's explanation for the photoelectric effect gained more and more experimental support. Soon, the idea that energy existed only in discrete chunks began to spread into other problems. Niels Bohr applied quantization to the structure of the atom in 1913. Classical physics predicted that electrons orbiting the nucleus would spiral inward and collapse, a disaster for matter itself. But Bohr proposed that electrons could only occupy specific energy levels, not any arbitrary path. They could jump between these levels by absorbing or emitting quanta of energy, but they couldn't exist in between. This was shocking. Atoms weren't miniature solar systems after all. They were something stranger, something more discontinuous, something deeply tied to Planck's original hypothesis. Without Planck's constant, the entire model collapsed. Quantum theory was beginning to emerge as something bigger, deeper, and more universal than anyone expected. By the 1920s, Werner Heisenberg, Erwin Schrödinger, and Paul Dirac had transformed Planck's quantum idea into a complete framework, quantum mechanics. Heisenberg's matrix mechanics and Schrödinger's wave mechanics showed that everything in the microscopic world, electrons, atoms, light, behaved according to quantized rules. There were no smooth transitions, no gradual changes, only jumps, probabilities, uncertainties. None of this would have existed without Planck's first step. To understand how radical this shift was, imagine being a physicist of that era. Your entire career was built on the assumption that nature is continuous. Every measurement, every experiment, every equation assumed that you could make a change as small as you wanted. If you turned down the brightness of a light source, you could do it infinitely smoothly. If you measured heat, you could reduce it in perfect tiny amounts. Now imagine someone telling you that this wasn't true, that nature had a smallest building block of energy, a minimum amount of change, a fundamental limit that nothing could go below. It was like telling a painter that colors didn't blend smoothly after all, but instead came in pixelated squares. It went against everything you believed. This is why the quantum idea was met with resistance. Planck's own reaction was mild denial. Einstein embraced part of the idea, but rejected the later introduction of quantum uncertainty. Bohr accepted the full quantum framework, but insisted it was not just weird, it was necessary. Heisenberg introduced uncertainty. Schrödinger hated the probabilistic interpretation, but contributed massively by forming wave mechanics. Every great mind of the era had a complicated relationship with the quantum revolution, yet none could ignore the fact that the revolution itself was rooted in Planck's quantum hypothesis. By the 1930s, the scientific world had changed forever. What Planck discovered without intending to was that energy quantization wasn't just a feature of glowing objects. It was a universal property of nature. It applied to atoms, molecules, light, electrons, vibrations, nuclear forces, everything. Once scientists accepted this, a flood of discoveries followed. Electron energy levels explained chemical bonding. Quantized vibrations, phonons explained heat. Quantum spin explained magnetism. Quantum tunneling explained nuclear fusion in stars. The entire cosmic machinery ran on quantized rules. The smallest components of the universe didn't behave like little billiard balls or miniature planets. They behaved like probabilistic waves that collapsed into definite states only when measured. All of these ideas were shocking and counterintuitive, but they were real, measurable, and beautifully accurate. The modern technological world is built directly on quantum theory. Planck himself could not have imagined the consequences his idea would unleash. Semiconductors, the basis of all computers, rely on quantum mechanics. Lasers, which power everything from medical equipment to barcode scanners, rely on quantized light. MRI machines use quantum magnetic properties. LED lights use quantum transitions inside semiconductors. GPS relies on precise atomic clocks that work through quantum energy levels. Even modern cryptography and quantum computing trace their origins back to Planck's original insight. It's not an exaggeration to say that without the idea of energy quanta, the entire modern world would collapse. Nothing from smartphones to the internet to aerospace engineering would look the same. The quantum revolution didn't just rewrite physics, it rewrote civilization. But beneath all this progress lies the remarkable truth that Planck himself didn't fully believe the idea he introduced. He accepted it mathematically, but he resisted its philosophical implications. This is perhaps the most poetic part of the story. A man who loved classical physics gave birth to the theory that destroyed it. A man who sought stability gave the world uncertainty. A man who wanted order unlocked the wildest behaviors known to science. Even decades later, Planck was still uncomfortable with the quantum leap he had made. He once admitted, "The introduction of the quantum was a purely formal step. I had no intention of revolutionizing physics." But history rarely cares about intentions. What matters is impact, and Planck's discovery was seismic. The idea of energy quanta forced humanity to confront a universe far stranger than we ever imagined. It forced us to let go of the comfort of classical intuition and embrace a world where probability rules, where particles can be waves, where certainty collapses, and where nature dances to the rhythm of Planck's constant. It forced us to accept that at the most fundamental level, reality doesn't behave the way our senses tell us it should. Because of Planck, the universe became bigger, deeper, more mysterious, and yet more understandable. His quantum hypothesis didn't just solve a scientific puzzle. It opened the door to a new era of discovery, one that continues to this day. Physicists still use Planck's constant as a key to unlock deeper layers of the universe. Modern theories like quantum field theory, the Standard Model, and even attempts to unify gravity with quantum mechanics revolve around the same quantized principles Planck introduced. Every time a particle is detected, every time a laser pulses, every time a quantum bit flips in a prototype quantum computer, Planck's idea echoes across the scientific landscape. When Planck introduced energy quanta in 1900, the world didn't understand what he had done. It took decades for the scientific community to grasp the magnitude of his idea. But today, we see clearly that this single insight didn't just fix a mathematical curve. It broke open the universe and revealed a deeper, more fundamental truth: that nature is quantized, discrete, and governed by rules far stranger than classical logic. Max Planck didn't just introduce a concept. He started a revolution that still shapes our world, our technology, and our understanding of reality. When we say Max Planck solved the problem of black-body radiation, it sounds simple, almost innocent. But behind that one sentence hides one of the biggest scientific crises of the late 19th century, a crisis so severe that it threatened to break the entire structure of classical physics. And out of that crisis emerged quantum theory, the most revolutionary idea in modern science. To understand the depth of what Planck solved, we have to travel back to the scientific world before 1900, back when physics looked confident, polished, almost perfect. Scientists believed they understood everything about heat, light, energy, and radiation. They believed nature behaved smoothly, continuously, and logically. But the black-body problem exposed the limits of this certainty in a brutal way. A black body is an ideal object that absorbs all radiation falling on it and emits radiation based only on its temperature. Heating a black body causes it to glow first red, then orange, then white, then blue. Scientists wanted to know, why does the glow follow this specific curve? Why does it emit more radiation at some frequencies and less at others? Why does the spectrum shift with temperature? This wasn't a small curiosity. It was considered one of the deepest questions in physics, a question that cut straight into the heart of thermodynamics, electromagnetism, and atomic theory. In laboratories across Europe, particularly in Berlin, very precise measurements of black-body radiation were being collected. These measurements were so accurate that any new theory had to match every twist and dip of the curve. And the curve was unforgiving. It had a very specific shape, low intensity at long wavelengths, rising to a peak, then falling rapidly at short wavelengths. The problem was that no known theory could match this shape. Scientists tried everything. Wien came close with his exponential formula, but it failed at long wavelengths. Rayleigh and Jeans developed their own equation using classical physics, but it exploded at short wavelengths, predicting infinite energy output. This horrifying result became known as the ultraviolet catastrophe. Imagine a world where everything around you glows with infinite ultraviolet radiation, blasting deadly light everywhere. Obviously, that wasn't happening, Yet classical physics insisted it should. The fact that the laws of physics predicted something so absurd meant something was deeply, fundamentally wrong. The Blackbody problem wasn't just a puzzle, it was a warning. Classical physics, for all its beauty, had reached a wall. Max Planck stepped into this crisis almost reluctantly. He didn't seek drama. He didn't crave revolution. But he had a deep fascination with the laws of thermodynamics and radiation, especially the concept of entropy. He saw the Blackbody problem as the perfect battleground to test whether the principles he believed in were truly universal. Planck tried every classical approach, every curve, every equation, every trick. Nothing worked. Then came the turning point. In 1900, Planck made a bold, almost desperate decision. He would derive an equation that matched the experimental curve at any cost. He didn't care whether the assumptions were crazy. He just needed a formula that reproduced the data. He was a mathematical warrior, and he was willing to go where the math led, even if it meant crossing the boundaries of classical physics. And that is exactly what happened. To get the formula right, Planck made one shocking assumption. The oscillators in the Blackbody cavity, tiny vibrating charges that emitted the radiation, could not change energy continuously. Instead, they could only change energy in discrete steps, or quanta. If an oscillator had energy, it wasn't E equals any value. It was E equals NHF, where N is an integer, F is the frequency, and H becomes Planck's constant. This was the birth of quantization. Planck didn't introduce this idea because he loved it. He introduced it because the math demanded it. When he assumed energy came in discrete packets, his formula finally matched the experimental curve perfectly at all wavelengths, at all temperatures. No other theory had been able to do that. His new equation, now known as Planck's radiation law, instantly solved the Blackbody radiation mystery. But the real miracle wasn't the equation. It was the interpretation behind it. By quantizing energy, Planck had broken the most sacred assumption of classical physics, the idea that nature was continuous. Classical physics believed energy could change smoothly, like sliding on a ramp. Planck replaced the ramp with steps. This small mathematical adjustment cracked open the universe, but Planck himself didn't yet realize what he'd done. At first, he thought of quantization only as a mathematical convenience, a temporary tool to make his curve work. But regardless of his intention, the mathematical step he took had enormous physical consequences. Here is why his theory solved the Blackbody problem. Classical physics predicted that oscillators in the walls of the Blackbody could take on any energy value. That meant there were infinite ways to distribute energy at high frequencies, and this is what led to the ultraviolet catastrophe. But Planck's idea restricted the possible energy values. No longer could oscillators emit tiny amounts of energy at extremely high frequencies. They needed at least one full quantum, HF. If they didn't have that much energy, they simply couldn't emit radiation at those frequencies. Suddenly, the infinite energy problem disappeared. The spectrum stopped exploding at high frequencies. Nature behaved again. Planck's quantum idea cut off the catastrophic pileup predicted by classical physics. It gracefully curved down the spectrum, creating a perfect match with the real, measured data. This was the moment physics was reborn. But even after presenting his formula, Planck hesitated. He wasn't ready to abandon classical traditions. He still hoped someone would reinterpret his idea in a classical way. But history had other plans. Einstein, followed later by Bohr and the architects of quantum mechanics, saw what Planck refused to accept. energy was truly quantized. The universe wasn't continuous. The Blackbody spectrum wasn't just a mathematical problem. It was evidence of a deeper truth about the structure of nature. Planck's quantum theory didn't merely solve the Blackbody radiation problem. It exploded open an entirely new way of understanding the universe. In the early 1900s, physicists still didn't realize how important this solution was. But with the benefit of hindsight, we can clearly see the Blackbody problem was the doorway into the quantum world. It was the place where classical physics collapsed and quantum physics began. Solving it required abandoning centuries of assumptions, rethinking the meaning of energy, and embracing a universe far stranger and more fascinating than anyone expected. By solving this one problem, Planck unknowingly initiated a scientific revolution. His quantum hypothesis didn't just patch a hole, it exposed an entire new dimension of physics. Planck's constant, usually written as h equals 62,607,015 times 10^3 joule seconds, might look tiny, almost meaningless at first glance. It's an unimaginably small number, and yet it sits at the heart of the most advanced, world-changing science humans have ever created. It is not just a constant, it is a doorway, a boundary line, a signature of how the universe actually works at its deepest level. When Max Planck introduced this constant in 1900, he had no idea that this little symbol h would grow into one of the most important building blocks of modern physics, shaping quantum mechanics, atomic theory, particle physics, electronics, cosmology, and the technologies that define our world today. To understand why Planck's constant became so important, you first have to understand what it represents. Planck discovered that energy is not continuous. It doesn't flow smoothly like water. Instead, it is released or absorbed in tiny, fixed packets called quanta. And the size of each packet is determined by Planck's constant, E equals hf, where f is the frequency of the radiation. This simple equation was a revolution. It said that nature itself has a minimum step size. You cannot give energy to an atom in any amount you want. It only accepts or releases energy in chunks proportional to h. That means h sets the scale for the quantum world, defining how tiny these energy packets are. The reason electrons jump between energy levels, the reason atoms emit specific colors of light, the reason matter behaves in stable patterns, all of it traces back to Planck's constant. Planck's constant also bridges the gap between waves and particles. Before quantum theory, physicists saw waves and particles as totally different things. Light was a wave, matter was particles. But with Planck's constant, Einstein showed that light behaves like particles, photons, each with energy hf. Later, de Broglie went further. If light can act like particles, then particles like electrons can act like waves. And he wrote their wavelength as lambda equals h/p, where p is momentum. Again, Planck's constant sits at the center. Without h, there is no wave, particle duality, no quantum behavior, no modern understanding of matter. Planck's constant also sets the scale for uncertainty in quantum physics. Heisenberg's uncertainty principle, one of the most famous results in science, states that you cannot perfectly know both the position and momentum of a particle. The limit of this uncertainty is determined by Planck's constant. Deltax delta greater or equal to h/4 pi, this is not a flaw in measurement. It is a law of nature. The universe itself refuses to be perfectly predictable at small scales, and the size of this unpredictability is governed by h. In a sense, Planck's constant defines how grainy reality is. A larger h would make the world more uncertain and more quantum weird. A smaller h would make the world more classical and predictable. The actual value of h is precisely balanced to allow atoms, molecules, and life to exist. In atomic physics, Planck's constant determines the allowed energy levels of electrons. Bohr's model of the hydrogen atom uses h to show why electrons occupy only certain orbits and never sit between them. This quantization makes atoms stable. Without h, electrons would collapse into the nucleus. That means matter itself, everything we touch, breathe, and see, holds together because of Planck's constant. In modern technology, Planck's constant is everywhere. Semiconductor physics, the science that makes computer chips work, depends directly on quantum mechanics, and therefore on h. Lasers work because of stimulated emission, a quantum process defined by Planck's quantization rules. LED lights, MRI machines, quantum cryptography, atomic clocks, GPS systems, and even the circuits inside your phone rely on equations that use h. Every time an electron moves through a transistor, every time a photon interacts with an atom, every time a superconductor carries current with zero resistance, Planck's constant is operating silently in the background. The importance of h became so fundamental that scientists eventually used it to define the kilogram itself. Since 2019, the kilogram is no longer based on a physical metal cylinder in France. Instead, it is defined using Planck's constant. That's how foundational it is. It anchors not just quantum theory, but the entire measurement system of physics. Planck's constant also appears in quantum field theory, the framework behind the Standard Model, the most successful theory in the history of science. All fields, particles, and interactions in the universe follow quantum rules set by h. When a particle pops into existence, when it annihilates into energy, when it exchanges force, carrying particles, the equations describing these events include Planck's constant. Without h, the mathematics of the universe falls apart. In cosmology, Planck's constant lies at the center of our understanding of the early universe. The Big Bang was dominated by quantum processes. The patterns we see in the cosmic microwave background, the fingerprints of the universe's birth, come from quantum fluctuations scaled by h. Even the structure of galaxies, stars, and planets traces its roots back to quantum processes controlled by Planck's constant. And perhaps most mind-bendingly, Planck's constant appears in the idea of the Planck scale, the smallest meaningful scales of space and time. Below these scales, classical concepts of space, time, and gravity collapse. Planck's constant, combined with the speed of light and Newton's gravitational constant, gives us the Planck length, Planck time, and Planck energy scales where quantum gravity must come into play. These values define the limits of our understanding and point toward future theories like string theory or quantum gravity. So why is Planck's constant a fundamental building block? Because it doesn't just appear in quantum mechanics, it defines it. It sets the shape of physical laws. It determines the behavior of matter and light. It marks the boundary between classical and quantum worlds. It governs uncertainty, structure, stability, and the behavior of everything microscopic. It powers our most advanced technologies and guides the deepest theories we have about the universe. Planck introduced h as a mathematical trick to solve one problem, but history transformed it into one of the pillars of modern science. Today, Planck's constant is more than a number. It is the signature of the quantum universe, the code written into the fabric of reality. Max Planck's pioneering work in the early 20th century marked the birth of quantum theory, a revolutionary framework that transformed our understanding of the physical universe. Before Planck's discoveries, classical physics, rooted in Newtonian mechanics and Maxwellian electromagnetism, reigned supreme. These classical theories offered powerful explanations for many macroscopic phenomena, but faltered when confronted with certain experimental results at the atomic and subatomic level. Among the most perplexing problems of the time was the issue of blackbody radiation, a phenomenon that could not be reconciled with classical predictions. Planck's resolution of this problem would not only solve an immediate scientific conundrum, but also provide the intellectual foundation upon which a new generation of physicists would build some of the most profound advances in modern physics. Planck introduced the revolutionary concept of energy quantization, proposing that energy is not exchanged continuously, as classical theories assumed, but rather in discrete packets, which he termed quanta. This bold hypothesis allowed him to derive a formula that accurately described the spectrum of radiation emitted by a blackbody, a perfect absorber and emitter of heat energy. What made Planck's idea extraordinary was not only its ability to solve the blackbody problem, but also its implicit challenge to the continuous nature of energy, a cornerstone of classical physics. By suggesting that energy exists in indivisible units proportional to frequency, Planck opened the door to a fundamentally new way of thinking about the microscopic world. It was this conceptual breakthrough that laid the groundwork for the work of subsequent physicists. Albert Einstein, for instance, extended Planck's quantum hypothesis to light itself. In 1905, Einstein proposed the notion of the photon, an individual particle of light whose energy is directly proportional to its frequency. Einstein's explanation of the photoelectric effect, an experimental phenomenon where light striking a metal surface ejects electrons, relied entirely on Planck's quantization concept. Without Planck's pioneering insight, Einstein might not have conceived of light as quantized, and the notion of wave-particle duality, which became a central pillar of quantum mechanics, would have lacked its critical foundation. Niels Bohr, another titan of early quantum theory, also built directly upon Planck's work. In 1913, Bohr introduced his model of the hydrogen atom, proposing that electrons orbit the nucleus only in certain allowed discrete energy levels, and that radiation is emitted or absorbed when an electron jumps from one energy level to another. Bohr's postulate of quantized orbits was essentially an application of Planck's idea of energy quanta to atomic structure. The precision with which Bohr's model could predict the spectral lines of hydrogen was unprecedented, and it provided compelling evidence that Planck's quantum concepts were not merely a mathematical convenience but a reflection of physical reality. Erwin Schrödinger, working in the 1920s, further extended the quantum framework by formulating wave mechanics, a mathematical description of the probabilistic behavior of particles at the atomic scale. Schrödinger's equations describe how the quantum state of a physical system evolves over time, encompassing Planck's quantization as an inherent feature of these states. The wave functions that emerge from Schrödinger's formalism rely on energy quantization to define discrete energy levels in atoms and molecules. Without Planck's initial insight into quantized energy, Schrödinger's elegant and comprehensive wave mechanics might not have emerged in the form we know today. Werner Heisenberg, another central figure in the quantum revolution, developed matrix mechanics, a fully quantum approach to describing physical systems. Heisenberg's uncertainty principle, which states that certain pairs of physical properties, such as position and momentum, cannot be simultaneously measured with arbitrary precision, is deeply rooted in the discrete, probabilistic nature of energy transitions, an idea first introduced by Planck. In essence, Planck's quantization principle set the stage for Heisenberg to reconceptualize the very limits of knowledge in the subatomic realm, revealing the counterintuitive and non-deterministic nature of quantum mechanics. The significance of Planck's work extends beyond the individual contributions of these later scientists. His ideas fundamentally reshaped the methodology of physics, shifting the field from a deterministic, classical world view to one that embraces probability, uncertainty, and quantization. Each of these subsequent physicists, Einstein, Bohr, Schrödinger, and Heisenberg, took Planck's initial insights and expanded them in ways that redefined the landscape of science. The quantum theory that emerged from their collective work underpins not only atomic and subatomic physics, but also chemistry, materials science, and even modern technologies such as semiconductors, lasers, and quantum computing. Moreover, Planck's legacy illustrates the iterative nature of scientific progress. A single conceptual breakthrough, such as energy quantization, can propagate through decades of research, inspiring new models, experimental techniques, and theoretical frameworks. By confronting the limitations of classical physics and daring to propose a radically new approach, Planck created the intellectual scaffolding upon which Einstein, Bohr, Schrödinger, and Heisenberg would construct the edifice of quantum mechanics. His work represents the spark that ignited one of the most profound transformations in scientific thought, a revolution that continues to challenge and expand our understanding of the universe today. In conclusion, Max Planck's groundbreaking discovery of energy quantization did far more than resolve the specific problem of blackbody radiation. It provided the foundational principle that enabled a generation of physicists to reimagine the atomic and subatomic world. The revolutionary ideas of Einstein, Bohr, Schrödinger, and Heisenberg, each a towering figure in modern physics, are deeply indebted to Planck's vision. Through his daring challenge to classical assumptions, Planck laid the cornerstone for quantum mechanics, reshaping the trajectory of science and technology and leaving an enduring legacy that continues to influence our exploration of the universe. The emergence of quantum theory in the early 20th century did more than revolutionize our understanding of the microscopic world. It also laid the foundation for a technological transformation that continues to define modern society. Concepts such as quantized energy levels, wave, particle duality, and the probabilistic behavior of particles, once considered purely theoretical, have become central to the development of devices and systems that power contemporary life. From the lasers in medical devices to the semiconductors in computers and smartphones, the practical applications of quantum mechanics permeate nearly every facet of modern technology. Understanding this influence requires tracing how the abstract principles of quantum physics were translated into tangible innovations that reshaped the technological landscape. One of the most significant breakthroughs enabled by quantum theory is the development of the laser. The concept of stimulated emission, predicted by Albert Einstein based on Planck's idea of quantized energy, underpins laser operation. In essence, a laser amplifies light by inducing atoms to emit photons coherently, meaning all the emitted photons have the same phase, frequency, and direction. This coherence is impossible to understand without quantum mechanics, as it relies on precise energy level transitions in atoms or molecules. The advent of the laser revolutionized a wide range of fields. In medicine, lasers allow for highly precise surgical procedures. including eye surgeries and tumor removals, minimizing damage to surrounding tissues. In telecommunications, laser beams carry vast amounts of data through fiber optic cables, enabling high-speed internet and global connectivity. Lasers are also critical in manufacturing, used for cutting and engraving materials with unparalleled accuracy, and in scientific research, where they serve as tools to manipulate and measure matter. At the microscopic level, the laser, therefore, is a direct application of quantum principles, transforming both industry and everyday life. Semiconductors, the backbone of modern electronics, are another technological domain profoundly influenced by quantum theory. Classical physics could not explain the behavior of electrons in solids, especially the existence of energy bands and band gaps that determine a material's conductivity. Quantum mechanics, through models like Schrödinger's wave equations and the concept of quantized energy levels, provided the framework to understand electron behavior in crystalline lattices. This understanding led to the development of semiconducting materials such as silicon and germanium, whose electrical properties could be precisely engineered by controlling impurities, a process known as doping. Semiconductors form the basis of transistors, diodes, and integrated circuits, which are the essential components of all modern electronic devices. Without quantum theory, the miniaturization of electronic components that powers computers, smartphones, and countless digital technologies would have been impossible. The ability to manipulate electron energy states at the quantum level enables the creation of faster, smaller, and more energy-efficient devices, fundamentally reshaping how society processes information and communicates. Beyond lasers and semiconductors, quantum theory has also transformed our understanding and development of electronic systems more broadly. Quantum mechanics explains phenomena such as superconductivity and the quantum Hall effect, which in turn have led to innovative technologies with wide-ranging applications. Superconductors, materials that conduct electricity without resistance at very low temperatures, are now used in magnetic resonance imaging MRI machines, particle accelerators, and magnetic levitation trains. Similarly, the principles of quantum tunneling, where particles can pass through energy barriers they would not overcome classically, are utilized in modern flash memory and tunnel diodes. These advancements would have remained elusive without the theoretical underpinnings provided by quantum mechanics, highlighting the inseparable link between fundamental science and technological innovation. Moreover, quantum theory is the foundation of the emerging field of quantum computing, which promises to revolutionize information processing. Quantum computers leverage principles such as superposition and entanglement to perform calculations that would be impractical or impossible for classical computers. In superposition, a quantum bit or qubit can exist in multiple states simultaneously, allowing for massive parallel computation. Entanglement, a phenomenon first noted in the Einstein, Podolsky-Rosen paradox and later formalized through quantum mechanics, enables instantaneous correlations between qubits regardless of distance. These quantum behaviors, rooted in Planck's initial insights, are already paving the way for advances in cryptography, optimization, and complex simulations in fields like chemistry and materials science. Quantum computing represents the latest stage in the long chain of technological innovations inspired by quantum theory, demonstrating that theoretical discoveries can eventually reshape entire industries. The impact of quantum theory on technology is not confined to cutting-edge research and specialized applications. It has also permeated daily life in countless ways. Devices such as smartphones, tablets, GPS systems, and LED displays all rely on semiconductors and other quantum-informed technologies. Even the simple act of capturing and displaying an image on a digital camera or streaming a video online involves layers of quantum-engineered components operating in concert. This ubiquitous presence underscores how a theoretical framework developed to explain atomic phenomena has cascaded into a global technological infrastructure, transforming how humans communicate, learn, work, and entertain themselves. In summary, quantum theory has profoundly reshaped technology by providing a framework to understand and manipulate the microscopic world. Lasers, semiconductors, and electronics all emerge directly from the principles of quantized energy, wave, particle duality, and probabilistic interactions. Each of these technological marvels demonstrates the powerful interplay between fundamental scientific discovery and practical innovation. From revolutionizing medicine and telecommunications to enabling the digital revolution and spearheading the development of quantum computing, the applications of quantum mechanics have become inseparable from modern life. The quantum revolution, initiated by Planck and expanded by Einstein, Bohr, Schrödinger, Heisenberg, and countless others, has thus not only changed our understanding of the universe, but also reshaped the very fabric of technological civilization, illustrating the profound and enduring impact of theoretical physics on human society. Max Planck's revolutionary insight into the behavior of energy at microscopic scales fundamentally altered our understanding of the natural world. Before Planck's work, classical physics reigned supreme, providing remarkably accurate explanations for macroscopic phenomena like planetary motion, fluid dynamics, and the behavior of everyday objects. Newton's laws of motion, Maxwell's equations of electromagnetism, and thermodynamics offered a coherent, predictable framework for scientists to understand how the universe functioned. However, as researchers began investigating phenomena at the atomic and subatomic levels, it became clear that classical theories could not account for certain observations. It was in addressing one of these anomalies, Blackbody radiation, that Planck made the groundbreaking discovery that energy is not exchanged continuously, but rather in discrete packets, which he called quanta. This discovery revealed that nature behaves fundamentally differently at microscopic scales than it does in the macroscopic world we experience directly. Planck's investigation into Blackbody radiation emerged from a scientific puzzle that had confounded physicists for decades. Experimental observations showed that the amount of energy emitted by a heated object did not follow the predictions of classical physics, particularly at high frequencies. The classical Rayleigh Jean's law predicted that energy output would increase without limit as frequency increased, leading to the so-called ultraviolet catastrophe, an impossible scenario where objects would radiate infinite energy. Planck's insight was to abandon the classical assumption of continuous energy emission and instead propose that energy could only be emitted or absorbed in discrete amounts proportional to the frequency of radiation. This was a radical departure from classical thinking. It suggested that at microscopic scales, energy does not flow smoothly, but rather in distinct, quantized packets. By introducing the concept of energy quanta, Planck fundamentally demonstrated that microscopic systems are governed by rules that do not mirror the deterministic behavior of macroscopic objects. At everyday scales, energy appears continuous because the quantization is so fine that it is imperceptible. A bouncing ball or a swinging pendulum seems to move smoothly, and heat flows from hot objects to cold objects in a gradual manner. However, at the atomic and subatomic level, energy changes occur in discrete jumps, and particles exhibit behavior that defies classical intuition. Electrons do not occupy all possible positions around a nucleus. Instead, they exist in defined energy levels. Photons of light are emitted as whole quanta rather than as a continuous wave. By demonstrating this, Planck revealed that the microscopic realm operates under fundamentally different rules, requiring a new theoretical framework, quantum mechanics. To describe it accurately, Planck's work illuminated several counterintuitive principles that characterize the microscopic world. One of these is the inherent discreteness of energy at small scales. Unlike the continuous flow of energy in macroscopic processes, quantum systems exhibit stepwise changes in energy. This discretization has profound implications. It explains the stability of atoms, the emission and absorption spectra of elements, and the very structure of matter itself. For instance, when an electron transitions between energy levels in an atom, it absorbs or emits a precise amount of energy corresponding to a photon of a specific frequency. This phenomenon is entirely invisible in classical physics, yet it is a direct consequence of Planck's quantum hypothesis. Another fundamental insight arising from Planck's work is the probabilistic nature of microscopic events. While classical mechanics allows for precise predictions of a system's future state, given complete knowledge of its initial conditions, quantum theory only provides probabilities. The exact time an excited atom emits a photon or the precise location of an electron at a given moment cannot be predicted with certainty. Instead, the laws of quantum mechanics describe the likelihood of these outcomes. Planck's quantization concept laid the groundwork for this probabilistic framework, highlighting a stark contrast between the predictable behavior of macroscopic objects and the statistical behavior of microscopic systems. Planck's revelation also introduced the principle of duality in nature, later expanded by Einstein and de Broglie. Particles such as electrons and photons exhibit both particle-like and wave-like properties, an idea that would have seemed absurd under classical assumptions. This wave-particle duality underpins much of modern physics, from the interference patterns observed in electron diffraction experiments to the behavior of light in optical devices. By showing that energy quantization is a fundamental property of nature, Planck effectively opened the door to recognizing that classical intuitions, smooth, continuous, and deterministic, do not apply at microscopic scales. At this level, reality is discrete, probabilistic, and often counterintuitive. The technological and conceptual ramifications of Planck's insight are immense. Quantum theory, built upon his initial discovery, has enabled the development of semiconductors, lasers, and magnetic resonance imaging. These applications exploit the unique properties of matter at small scales, properties that would remain hidden under a purely classical perspective. For example, the operation of a laser relies on the precise, quantized energy transitions of electrons in atoms, while semiconductors depend on the controlled movement of electrons between quantized energy bands. The modern electronics and photonics industries owe their existence to Planck's demonstration that the microscopic world follows fundamentally different rules from the macroscopic one. Furthermore, Planck's work reshaped philosophical and scientific perspectives on nature itself. By showing that macroscopic intuitions do not extend to the quantum realm, he challenged long-held assumptions about determinism and continuity in the universe. Nature, at its smallest scales, is not a smooth, clockwork mechanism, but a realm of discrete events governed by probability. This recognition required scientists to develop new mathematical tools, experimental techniques, and conceptual frameworks culminating in the full development of quantum mechanics by Bohr, Heisenberg, Schrödinger, and others. The paradigm shift initiated by Planck's quantization principle thus fundamentally altered both scientific thought and our broader understanding of reality. In conclusion, Max Planck's discovery that energy is quantized revealed that nature behaves differently at microscopic scales, defying the assumptions of classical physics. By introducing the idea of discrete energy packets, Planck showed that microscopic systems operate under rules that contrast sharply with the continuous, deterministic behavior observed in everyday life. His work provided the foundation for quantum mechanics, highlighting the probabilistic, dual, and counterintuitive nature of the atomic and subatomic world. Beyond its theoretical significance, this insight has had profound technological and philosophical implications, influencing everything from modern electronics and lasers to our fundamental understanding of the universe. In revealing the hidden order of the microscopic realm, Planck transformed the way humanity perceives and interacts with nature at its most fundamental level. Max Planck's discoveries at the dawn of the 20th century did more than resolve a single scientific anomaly. They ignited a profound transformation in our understanding of the physical universe, marking the beginning of the quantum revolution. At a time when classical physics seemed nearly complete, Newton's mechanics had accurately described motion for centuries, and Maxwell's electromagnetism had unified electricity and magnetism into a coherent framework. The behavior of microscopic systems posed puzzles that resisted conventional explanations. Planck's bold introduction of quantized energy provided the first key to these mysteries, shattering the centuries-old notion that the universe is entirely deterministic and continuous. This pivotal insight launched one of the most significant scientific revolutions in history, reshaping both the conceptual foundations and technological applications of physics in ways that continue to resonate today. The context for Planck's groundbreaking work was the problem of blackbody radiation. Classical physics predicted that an idealized object, a blackbody, would emit energy at increasingly higher rates as the frequency of radiation increased, a prediction known as the ultraviolet catastrophe. This result was nonsensical. It suggested that objects would radiate infinite energy at high frequencies, clearly contradicting experimental observations. Planck's radical solution was to propose that energy could be exchanged only in discrete units, or quanta, proportional to the frequency of radiation. By introducing the constant HHH, now known as Planck's constant, he created a mathematical framework that accurately described observed spectra and resolved the ultraviolet catastrophe. This single step, though initially intended as a practical solution to a specific problem, planted the seeds of a revolutionary paradigm shift. Planck's quantization concept challenged the deeply entrenched assumptions of classical physics. For centuries, scientists had believed that energy, matter, and even time were continuous and could be divided indefinitely. Planck's work demonstrated that at microscopic scales, nature is fundamentally different. Energy comes in indivisible packets, atomic systems obey discrete energy levels, and phenomena occur probabilistically rather than deterministically. This revelation required physicists to rethink the very foundations of their discipline. It inspired a wave of theoretical innovation, leading directly to the development of quantum mechanics by pioneers such as Albert Einstein, Niels Bohr, Erwin Schrödinger, and Werner Heisenberg. These scientists extended Planck's principles to light, atoms, and subatomic particles, constructing a fully coherent framework that could describe previously inexplicable phenomena like the photoelectric effect, atomic spectra, and the behavior of electrons in solids. The quantum revolution initiated by Planck also fundamentally altered the philosophy of science. Classical physics had offered a predictable, clockwork universe in which every event could, in principle, be calculated from initial conditions. Planck's discoveries introduced a universe where uncertainty, probability, and discrete transitions play essential roles. The notion that reality at its most fundamental level defies intuitive expectations was not just a technical adjustment, it was a conceptual upheaval. It reshaped the way scientists think about causality, measurement, and the nature of reality itself. The philosophical implications were profound. Reality was no longer fully knowable in the classical sense, and observation itself became an integral part of understanding physical systems. This conceptual shift reverberated through physics, philosophy, and even broader intellectual culture, cementing the quantum revolution as one of the most significant paradigm shifts in scientific history. Technologically, the implications of Planck's discoveries were just as transformative. Quantum theory, born from his insights, laid the foundation for technologies that define modern life. Semiconductors, lasers, magnetic resonance imaging, and quantum computing all rely on the principles first uncovered by Planck. For instance, the operation of a laser depends on precise, quantized energy transitions in atoms, and semiconductors exploit discrete energy bands to control the flow of electrons. These applications were unimaginable in a classical framework and highlight how Planck's theoretical work catalyzed a practical revolution, creating technologies that have reshaped communication, medicine, and industry. In effect, the quantum revolution sparked by Planck's discoveries has had both intellectual and societal impact, illustrating the extraordinary breadth of his influence. The revolutionary nature of Planck's work also lies in its cascading influence on subsequent generations of scientists. Albert Einstein, inspired by Planck's quantum hypothesis, proposed the photon theory of light and explained the photoelectric effect, earning the Nobel Prize for his contributions. Niels Bohr applied Planck's ideas to develop his model of the atom, demonstrating the quantized nature of electron orbits. Schrödinger and Heisenberg built on Planck's concepts to formulate wave mechanics and matrix mechanics, respectively, providing a complete theoretical framework for quantum mechanics. In each case, Planck's initial insight served as the cornerstone upon which an entirely new understanding of the universe was constructed. The quantum revolution was not the work of a single individual, but Planck's discovery was the spark that ignited it. Furthermore, Planck's role in this revolution exemplifies how theoretical breakthroughs can profoundly reshape human knowledge. He did not set out to overthrow classical physics. Rather, he sought to solve a practical problem. Yet his willingness to embrace a radical idea, quantized energy, demonstrates the transformative power of intellectual courage and creativity. The quantum revolution shows that fundamental science is not merely a tool for solving isolated problems, but a means of redefining the very nature of reality. Planck's work serves as a reminder that the most profound scientific advances often arise from questioning assumptions and exploring ideas that initially seem counterintuitive or implausible. In conclusion, Max Planck's discoveries did not merely extend the frontiers of physics. They launched a revolution that redefined our understanding of the universe at its most fundamental level. By introducing the concept of quantized energy, Planck challenged classical assumptions, solved long-standing puzzles, and opened the door to a new era of theoretical and technological innovation. His work paved the way for Einstein, Bohr, Schrödinger, Heisenberg, and countless others to develop quantum mechanics, fundamentally altering both science and society. The quantum revolution remains one of the greatest scientific transformations in history, and at its heart lies Planck's visionary insight that the microscopic world operates according to principles dramatically different from those observed at macroscopic scales. Through this discovery, he not only reshaped physics, but also changed the trajectory of human knowledge, technology, and our understanding of the universe itself.